Okay, this video is going to cover our last section of chapter 18, talking about Lewis acid-base theory. You can see this diagram I've drawn on the right-hand side of the image here. This is going to kind of lead into why we're going to very briefly discuss Lewis acid-base theory here at the very end of this chapter. We've already talked about one main type of acid-base theory, and that's Bronsted-Lowry, or BL here in this example. The Bronsted-Lowry acid-base theory covers a pretty broad amount of acids and bases, and more specifically, it covers almost all of the acids and bases that we use in water. So remember, a Bronsted-Lowry acid is a proton donor. So let's just write that here. A Bronsted-Lowry acid is a proton or H plus donor. And we're going to, right here, write down what a Lewis acid is here in a minute. So just leave yourself some space. And then down below that, let's remind ourselves what a Bronsted-Lowry base is. If a Bronsted-Lowry acid is a proton donor, then the Bronsted-Lowry base is a proton, and again that's H+, acceptor. So this works really well in water because in water we're transferring a proton around and we're using water as the carrier for that proton. In Arrhenius acid-base theory, we didn't really even talk about Arrhenius acid-base theory because it only covers a very small set of acids and bases, specifically anything that donates a proton or gives up hydroxide in solution. So this is a very limited number of acids and bases that we could talk about. The Bronsted-Lowry theory was actually created in order to better describe some of the things that we were seeing in water where a solution of ammonia was actually basic because ammonia can accept a proton and make hydroxide in the solution. So it wouldn't be an Arrhenius base because it's not giving up hydroxide, but it can still make hydroxide in solution. So Bronsted-Lowry covers a wider range of bases that we would want to talk about in water. Now, again, we just talked about solvent leveling in the other video, so now we can start thinking about acids and bases in different solvents. And this would be a focus of organic chemistry later on, is looking at how acids and bases work when they're not in a water-based solvent. So we would call that an aprotic solvent. So this is where Lewis acid-base theory comes in, and Lewis is a very general definition for acids and bases, and it basically covers almost all of the acids and bases that we would talk about, whether or not it's in water or not in water. And either way, as you can see, Lewis acids can still describe Bronsted-Lowry acids. So a Bronsted-Lowry acid is a proton donor, and kind of what we've seen from that, before we go on to our definition, and I forgot to write this, we're going to write in what a Lewis base is. Before we go on, let's kind of look at an acid-base reaction again. We've got ammonia, NH3, and it has a lone pair. And we're going to dissolve that in some water. So this is just going to show that Lewis acid-base theory still works for Bronsted-Lowry acids and bases. This is an equilibrium, and of course didn't give myself enough room. Let's move this over here. Better than erasing a whole chalkboard. We end up with the Bronsted-Lowry base in this case. So this is a Bronsted-Lowry base. It's our weak base. And this would be a Bronsted-Lowry acid. So the base is going to be accepting a proton. And the way we kind of denote that is that this lone pair goes out and grabs onto that proton. That pair of electrons goes back onto oxygen, and we end up with NH4 ammonium with a positive charge and hydroxide with a negative charge. So in the Bronsted-Lowry case, the Bronsted-Lowry base is accepting the proton, so it's accepting that proton from water, and the water is donating a proton, so that makes it the acid. A Lewis acid is defined as a lone pair acceptor. And a Lewis base, similarly, is a lone pair donor. And by lone pair, we mean lone pair of electrons. So let's go back and look at our Bronsted-Lowry acid and base Here in this example, we can see the ammonia is a Bronsted-Lowry base because it is donating or it's accepting a proton, whereas in this case, it's donating a lone pair. So that means it's also a Lewis base. And we can go back and see that a Lewis acid is a lone pair and acceptor, and as you can see, the water molecule is accepting that lone pair from the ammonia, or you can think of it as the bond that it's breaking with hydrogen moves a lone pair back onto the water. Either way, it's accepting a lone pair. That makes it a Lewis acid. In general, the Bronsted-Lowry acid and the Lewis acids are both going to be the same because a proton donor also has to accept a lone pair. So we can kind of make a little amendment here and say that up here up top in red, we can say all Bronsted-Lowry acids are also Lewis acids. With a Bronsted-Lowry base, that's a proton acceptor, and in this case it's going to be looking as a Lewis base. It's looking as a proton donor. We're not going to make a generalized statement about that because there's a couple other examples that kind of break this rule, but let's just look at another example. If we have boron trifluoride, it's going to take a trigonal planar shape. Boron is, in this case, a little bit electron deficient. It wants some electrons. So if it's going to be accepting some electrons, that means it's probably going to be acting as the acid. So let's just finish this reaction and then we'll kind of see what that case is. And ammonia is going to come along with its lone pair. We're going to look at the reaction between these two. Now again, the boron wants some electrons and nitrogen has a free lone pair, so it's going to donate those electrons onto the boron, and we're going to form a chemical reaction where we have a bond between the boron and the nitrogen now, with the hydrogen still there, and let's not get our stereochemistry mixed up here. Oops. So this is more of an example of what you'll encounter when you get into organic chemistry later on. But what we have here is we have the boron trifluoride is accepting a lone pair. So by our definitions, that means it's the Lewis acid. And the nitrogen is donating a lone pair, making it the Lewis base. And the result of this type of reaction is called an adduct. So we've made an adduct. And as you can see, this is not involving any protons at all. We haven't moved any protons, created any hydroxide or hydronium, but we can still classify this as an acid-base reaction between a Lewis acid and base, making an adduct. This is actually just a more simplified general approach to talking about any kind of chemistry in general. And what we can talk about from this type of perspective is that most chemistry is going to be some type of Lewis acid-base reaction. So you can see back here, Lewis acids and bases pretty much covers the whole spectrum of chemicals. So if we go back to our little diagram here, Lewis acid-base theory covers most of the chemical reactions we deal with. Bronsted-Lowry covers a lot of the acid-base reactions we deal with in water and includes things like ammonia, which really don't give up hydroxide, but they still make hydroxide by accepting a proton, whereas Arrhenius is the most limiting case because it only allows for talking about hydronium or hydroxide, which only really happens in water. So there's our three definitions talking about Bronsted-Lowry and Lewis acid-base. We really didn't talk about Arrhenius. I won't be asking you about that on the exam. We'll mostly be focused on Bronsted-Lowry. That's where all of our calculations have been based. And Lewis acid-base is more of just being able to recognize what's a Lewis acid and what's a Lewis base. And just to summarize quickly, a Lewis acid typically is electron deficient and wants electrons. A Lewis base typically has extra electrons to donate. So as you work through some of your practice problems, you can always go back and see some of these things that we've classified as a Bronsted-Lowry acid base. Go back and see, can you classify them as a Lewis acid or base, and get that practice.